present, for the workshop for the month. It's the last talk of the entire month. It's going to be Santosh Vempala from Georgia Tech.
Thank you. Thank you for staying for the last talk. And there is an exciting discussion to come after, so it won't be all in vain. This talk is not so much about consciousness, so I invite you to not stay conscious. Feel free to rest, sleep before. Yeah. But it is about a very interesting problem, coin flipping in the context of the brain. It'll take me some time to set it up, but I promise to finish by 5, so it is 25 minutes from now or earlier. So, yeah. Okay, so. Okay. All right. 24 minutes. Maybe should I unplug and. No. That counts like 2 minutes. Okay. Hopefully. Yes, excellent. Thank you. So I'm going to step back a little bit. I know that many of you are not theoretical computer scientists also, although by now maybe you are. We didn't start out before the week. So what is computation? Step back. Nothing to do with computers, but rather it's a well-defined sequence of state changes. Okay? You can ignore the parenthetical remark. So there's state, which is memory, input, output, and it's changing according to some rules, and that's computation. And if you take this broad perspective, we still have a notion of what is computable. And so this, as Lenore mentioned, is a Church-Turing thesis, that anything computable can still be computed by a Turing machine. Maybe not as efficiently by some other means, but it can be computed. Okay, and the Turing machine is a finite state machine plus tape, infinite memory. Great. Computation is universal when it's in this sense. So there are planetary systems. Where will the Earth be tomorrow? Weather, is it going to rain here at this spot? Networks in your body, ant colonies, and of course, brains. There's state and change of state. And so from my perspective, here's what the brain is. And this is to give you the caricature version of what a TCS person or a random TCS person might think of this entire sophisticated field. So, okay, so give you a theory of mind of me. Yeah. So it's a network of 80 billion neurons, 1,000 to 10,000 connections per neuron. These synapses, these connections have variable strengths. New ones can form and existing ones can disappear during lifetime. Great. Individual neurons spike or fire based on some activation rules. And these are functions of signals on their input synapses. They're nonlinear, typically. A common model is a threshold. If it exceeds some threshold, it fires. But there are over 1,000 different types of neurons. So it's not the only one. And these signals, this firing has a temporal aspect with rates, firing rates, and patterns. That's it. I'm going to keep it at this level. Okay. So then the question, which I think is maybe one of the biggest, nicest questions in science today, is how does the mind, perception, cognition, emerge from the brain? So I'm kind of summarizing the month, I suppose. Neurons and synapses, right? And as far as I know, there isn't a good explanation. Satisfactory explanation. Certainly, I don't know one. So, despite all this fantastic, striking progress in neuroscience and century-plus insight in cognitive science, there isn't an overarching theory. There's no evolution. There's no, relativity or quantum mechanics. Okay. So still, we should think about it. And so what's the right level? Should we think about the whole brain, neurons and synapses, dendrites? Very interesting things happen at all these levels, even molecules, or maybe somewhere in the middle. So this model that you've seen a couple of times, and I will take the opportunity to conclude this workshop with a precise summary of the model and some things that maybe you didn't see derived from it, is a formal probabilistic model of the brain. We'll leave everything will be well defined. It's going to be implementable by neurons and synapses. It'll be consistent with basic principles of neuroscience. It's not going to be an accurate model of everything we know, but it will be consistent with the most basic principles. And it's inspired by early work of Les Valiant, who was modeling the brain several decades ago. So before I do that, here's some very basic thing. We're going to model the connectome itself, just the underlying connections as a random graph. Okay. So by random graph, I mean the classical Erdős-Rényi model, where you have n vertices and the edge probability is p. Every edge occurs independently with probability p, whether it's present or not. So if p equal to 0 is the empty graph, p equal to 1 is the complete graph. It's a great basic model with surprising structure, in the sense that, for example, the maximum degree is concentrated, the maximum clique size is concentrated. Perhaps surprisingly, any property that's monotone with as the probability increases. So for example, does the graph have a cycle that goes through all vertices? Is the graph connected? These properties transition sharply from probability 0 to probability 1. And in what we're going to use as a model of the connectome is a directed GNP. So the edges are directed, but each one occurs independently with probability p. Okay. This is a simple, unrealistic, admittedly unrealistic, but nevertheless useful model of the connectome. You can certainly consider departures from it, and people do, and we do. Okay, so having that in mind, in the next 2 slides, I'll restate the model. So if you've seen it and have some questions, or if you haven't seen it, here it is. So the brain, so this is the model of the brain. It has a finite number of brain regions, 10, 12, a constant number of brain regions, areas. Each of them contains n neurons. N is a parameter. This could have varied from area to area, but we'll just call it the same n. It won't matter for what we'll be deriving. Okay, n neurons in each area. Within each neuron, so neurons can fire or not fire. Within each area, only k out of the n are allowed to fire. Think of k as square root n, if you like. Okay? Only k of them fire at a given time, not all n, only k. This is an abstraction of inhibition, and I'll mention later that in fact it can be implemented completely locally. Now, the areas themselves, not every pair, but some pairs are connected by directed random graphs. So whether a neuron here is connected to a neuron here is determined by probability p independently for every pair. All areas are recurrently connected internally. So there are, again, that's a random graph with probability p. So you've got these areas that are random graphs, and then some pairs of areas are connected either just in one direction or both directions. That's the connectome. And I also mentioned one aspect of the dynamics, that only k are allowed to fire at every time step. Okay, now this neurons fire in discrete steps. We alluded to that, I'm making it explicit. Only k neurons, which k? It's the k that have the highest total input from the previous round. So a neuron here, out of these n, look at the k, for every neuron there's input coming not only from its own area, but possibly from other areas. So each neuron has a total input. Look at the top k in each area, and those are the ones that fire. Okay, there's k firing in each area. That's the firing mechanism. Now, connections between areas, even if they exist, can be inhibited or disinhibited. So there is a mechanism by which you can say this area, even though it is connected to that area, is not allowed to affect it right now. Okay, you may suspend the effect of one area to another. And then finally, there's plasticity. This is how the weight, so connections also have weights. We'll start out with just all 1. You could start random, but 1 is just as good for the purpose of what we'll derive. And these weights change in the following fixed way. If a neuron I fires, followed by j, then the connection from I to J, the weight increases. Okay? This is just basic Hebbian plasticity. You could do this either additively or multiplicatively, and that's basically it. They're more convenient in different contexts, but both of them work for everything we'll derive here. The last thing, in case you're worried, oh, you're only increasing weights, they're going to blow out of proportion. There's a mechanism, we'll refer to it as homeostasis. All it does is every once in a while, not every time step, every once in a while, it renormalizes the total input weight to each neuron so that the total weight is, say, 1. So you just keep the sum of the weights are all positive here, non-negative here, and so the total weight you keep it at 1. Okay, that is the entire model. I have not left out anything of the dynamics or the creation of the substrate. Great. Okay, so here's the question. Given this model, will computation and learning emerge rather than have to be programmed? There's no, notice, this is it. There's no backprop, no gradient descent, no global coordination. There's no data type or programming language. So then I have to ask, how does the brain even create and recall memories? You have to do something here, right? Where is this happening? If this is the brain. So let me start with that. This is going back. Yes. Yes. So we model input. Great. The input itself, we can think of it as an area of the brain. So, for example, if it's smell, odor, there are neurons for different receptors for different odorants, and they fire. So it's again, which subset is firing indicates a particular stimulus. If it's visual, there's a whole bunch of neurons for a visual area, and some subset of them fire. Yes. Oh yeah. So we know now that about 40% of all neurons are inhibitory, and so we think of it as, so there are all these recurrent areas. Let's take one of these areas. How do we enforce the top K? We have a corresponding set of inhibitory neurons, which are connected only to these, and these are connected, so it's a bipartite graph between these two. And the point of the inhibitory neurons is when they get activated when they get sufficiently input, and then they send a negative signal to whatever they're connected to. So it's a bipartite graph where the excited neurons, when they get excited, they will send to themselves, but also to the inhibition. And the inhibited neurons, when they get excited, will send negative signals to the excited neurons. It's random, PK. Yeah, there's a wide range when it works. Square root seems to be very nice for various convergence properties. There is one crucial element for this to stabilize quick. So what this does, the theorem about this is that if the inhibited neurons integrate, meaning react a constant times faster than the excitatory neurons, it turns out this is a fact from neuroscience, which we didn't know, but realize that's necessary for the stability. Then within a very few steps, it stabilizes to a fixed fraction of the n neurons firing.
I don't understand this. K is about square root and the degree is square root and would you need at least square root and such to pick the top K? Just information here.
I'm not sure. Yeah, sure, but yeah, I can show you that mechanism. Yeah, no problem. Yeah, okay. So we're asking what happens. Will memories emerge? And there has been an indication of what these memories should be. So there are subsets of neurons. A memory is encoded as just a subset of neurons that fires together in response to a particular concept, person, name, or even a more general thing. A workshop. And they've been referred to as the alphabet of the brain. And the hypothesis is that this is the intermediate level of brain computation. It's implicated in higher cognitive functions, and these are the data types. But the point I'm going to focus on is that they actually emerge in this model. You don't have to program them. How is this? What are we talking about? So in the stimulus area, some subset of K is firing. Maybe you're smelling something. And as a result, because of the connectivity, the top K in this area, some next level area in the brain fire. Great. Now in the next step, we have both the input and this top K firing. That leads to a second top K, not necessarily the same. And then these fire, and that leads to a next top K. Okay, so this could go on for a bit, except we also have Hebbian plasticity, which is strengthening connections between I and J if I fired and then J fired. And the point is that this combination is enough to quickly stabilize this subset that's firing, so that the next time the same stimulus comes, immediately you go to this last one, the stable one. That's the memory. So what happens here is that the projection process converges exponentially fast with high probability. The high probability is over the choice of the random graph. That's the only probabilistic aspect so far. And the total number of cells involved in the entire neurons involved in this entire convergence process is only a little bit more than K if the plasticity, the factor by which we're increasing the weight, is more than a certain threshold. And as long as it's positive, it will still converge, but you'll use you could potentially use a large number of steps. And the parameter, the lower bound, I mean, this suffices. We don't know the precise answer, but this suffices. P is the edge probability, K is the subset size. So all of this is like a constant for reasonable choices of P and K. Okay, so so we didn't do anything. We just ran the model by presenting a stimulus a few times. That creates a memory. You can do this for many different objects. Great. This is just a simulation of what's happening, and in about a dozen steps, you don't create any more new cells. I wanted to mention there's something nice about why this happens, and it's not obvious. This winner's take-all process, why it converges quickly. But since I have 9 minutes, I will just say that there is a competition between the previous winners and a large pool of random choices. And this competition, it could go either way, but because if the plasticity is high enough, it starts favoring the previous winners, and they win out very quickly. That's the point. Yeah, so you can determine the thresholds and the number of iterations precisely. So now you get the next nice thing you get. Yes, your future presentation of the same stimulus fires the same assembly. What about firing just a subset? You don't see the whole smell, you see some part of it. What happens next? So, and this is what we call pattern completion, or what's called pattern completion. So if this assembly that you created is strong enough, if its interconnectivity is high enough, then just firing a subset of it, say 10%, will very quickly fire the entire thing. You see a little bit of an image, and you predict the whole thing, you recognize the whole thing. And for this to happen, we just need that the stimulus is presented sufficiently many times for any small enough epsilon. Okay? And then connectivity internally is large. And this is a benefit of recurrent connections that you don't see in, say, insects, for example. Okay, the next one is again in neuroscience, very quickly. If you see two stimuli co-occurring, you see Manuel and Lenore and Avram together. I see them together in Pittsburgh, see them together in Berkeley. Next time I see Manuel, I say, where is Avram? Right? Okay. And indeed, what happens in the brain is that I already have assemblies for them. They actually overlap more. They drift and overlap more. This is an experimental finding in human subjects, confirmed several times now. But this happens provably in this model with just the GNP association. And as I mentioned, it's also verified by neural recordings. Great, but can this do more? So far we have storage and retrieval, also of near neighbors, and these things. How about learning? So how do brains learn? I mean, this is an important question. Seems unlikely they're doing gradient descent or anything so global. And so here's one way we can think about it. So if I present this bottle to you 10 times, you have an assembly for this bottle. What if I give you another different kind of bottle, a third kind of different kind of bottle, a fourth different kind of bottle? You create an assembly for the notion of bottle. Will that happen in the model? So the way we model this, say there's a distribution of one type, and then there's a distribution of a different type, and maybe a third distribution, and so on. And you'd like to create a higher level assembly representing this somewhat closely knit set of objects that come from a distribution. So here's how we set this up. Well, let's just take the simplest case where it's 2, And the separation between them is a half space. There is some linear combination of features which puts one category one side of the half space, the other category in the opposite side, and there's a margin. There is a margin between the two. That's important in this case. And all we do, so remember, there's no labels. All we do is present examples from one side, but consecutively, all positive examples first, then all negative examples. That's it. And guess what happens? It actually creates an assembly for each of them. So this is the neurons that are firing in response to a new positive example. And these are the neurons firing in response to a new negative example. And there's almost no overlap. If you look in the feature space, they overlap almost the same, because the only thing they're different along is one direction with a margin. Whereas if you look in the space where they've created the assemblies, there's much less overlap. Again, nothing special. We're just running the plasticity experiment. I mean, the simulation. This is provable. This is a theorem for sufficiently large margin. No, they are. The features are. Oh, yes. If the presentation is intelligent, there's no guarantee. Yes, it's very important. So that's the weak way in which we're getting labels. We're seeing positive, 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 enough that it creates an assembly of the distribution. Yeah. Okay, the next step, which we saw alluded to by Max, sequences. These seem to be very crucial to brains. The fact that we're very good with sequences, A, B, C, D, songs, poems, etc. Pointers, as Manuel referred to in his talk. And these sequences are observed in experiments. There's cell assembly sequences in the rat, where they run through maze in complicated ways, and they play out the sequence of assemblies before they run through it. There's a pre-play. And so what's going to happen in this model if I present to it not one stimulus, but a sequence, and I do it a few times, A, B, C, D, A, B, C, D, and so on. Well, the nicest thing happens, it creates an assembly sequence that's linked, so that if I now play or present the first one or any prefix, it'll play out the rest of it. Right? That's what happens in the model and in simulation and as a theorem, but you have to present it for the theory. We represent the sequence log n times. In practice, we present it 5 times. Okay, so once you have sequences, you have powerful consequences. You can now learn finite state automata because we simply present all the transitions a few times. This is a very helpful trainer. We're not trying to ask you to learn it just in some cryptic way. We're telling you, here is the state, next state, and then here's the state, here's the next state. And then once you can learn Turing machines, finite state automata, you have Turing machines, except you have to do a tape simulation as well. Turns out you can do it. So this is just a completeness theorem. We're not saying the brain is representing Turing machines, but it is giving you a way to learn algorithms. But how do you learn algorithms? Well, you have to learn the finite state machine. How do you learn the finite state machine? You see every transition a few times. So this is also a theorem. In practice, how we actually implement this is there's a symbol area, a state area, and a transition area. And these things are activated when the symbol is presented, when the state is presented. And together they activate the transition, which is created. This we don't know about in advance. We only create this because we see the symbol next. And this gives you a way to learn a general finite state automaton or Turing machine. Okay. An important aspect of this, getting this to happen, is that we need areas to fire alternately. So when this area A is firing, and a different area B should not be firing. Turns out that this mechanism can be achieved in at least 2 different ways. I'll skip this slide. This is the precise way in which it's implemented with inhibited neurons to get this alternation to happen. But basically, you can either do it with long-range interneurons or brain rhythms. Either one is sufficient. And so all of this computation that I mentioned to you is emergent. You just present the appropriate sequence of stimuli, and it results in the creation of this representation of the phenomena you're seeing. So one way to think about it is that in Mars 3-level framework, we no longer have the algorithm part. There's the input, and there's the functional description. You don't need an algorithm. All the brain areas do what they should do, and you have the state happen. So the model is deterministic so far. It's only in the initial graph. Everything else I described is deterministic. So this is completely predictable, and this is not so interesting, right? How does the brain learn statistics? Which arm should I pull? What should I say next? So, and then, whereas recording statistics is very natural, when you see A, let's say you either see B or C half the time. You toss a coin, you either see heads or tails half the time. So next time you toss a coin, you want to say it's half or 1/3 or whatever it was. So as far as the recording is concerned, it seems natural. You present A and then you present B, that those set of synapses are strengthened. You present A and then you present C, those sets of synapses are strengthened. But now if you fire A, how does it choose randomly? How do you simulate a coin flip? Okay. So what we're going to take advantage of is the noise in the brain. The model will say, well, let's perturb the total input to each neuron by a small Gaussian. That's it. And then we still choose the top k. Okay. So total input to each neuron is perturbed by a small Gaussian and choose the top k. Fine, good. That's the model. Now, how do you flip a fair coin? Remember, we can't use, what I want to do is choose assembly A or assembly head or tail with 50-50 chance. Let's say, it could be any probability. We can't use one of these really nice tricks like von Neumann's trick where you toss whatever noise you have twice, and if it's head tail, it's a head. If it's tail head, it's a tail. Otherwise, you try again. Can't do that. We can't use the telephone. Sorry, man. Which this is a fantastic thing that inspired a whole 44 years of crypto, 44 decades of crypto. But what do we do? So here's what we'll do. So this is the setup we have. We have the weights coming in here have been strengthened. The weights coming here have been strengthened just because you saw it enough. Weights internally are strengthened because it's an assembly. Internally are strengthened. Everybody else has weight 1. Now, let's say the input fires. We let CT be the kth cap, which means, first time S fires, some subset fires. It may not be H or T. Fine. And then second time, some other subset fires. But we want this quickly to become either H or T. That's all we're saying. If you now fire S, it'll quickly resolve to H or T. In fact, the probability that the subset it converges to is H, and this you could replace with T, is very close to 1/2. And the number of steps, I haven't written it here, is about log K over log KP. Logarithmic number of steps. Yeah, so I would like to tell you about the proof. I'd like to tell you much more, but I know I'm over time. So all I'm going to say is that you can use, there is a map from weights internally to the assemblies to firing probability, to the probability of choosing. It's a monotone invertible map. So you can, with a very simple, if you make the plasticity rule slightly more complicated than Hebbian, it's still local, it's for each synapse. But we don't want, it's not just uniform. When the weights get high enough, you have to slow down the weight increase. That's the small change you have to make. If you do that, then you can actually get your statistics to be correctly represented in the brain by just plasticity. Okay, so once you have this, you can do probabilistic finite automata because you can now model transitions. And that's the theorem about that. For Markov chains of out degree 2, you can approximate the probabilities just by presenting the input sequences from this Markov chain, nothing else. Of course, max out degree 2, you can take any Markov chain, convert it to out degree 2 by branching up, by replacing the out edges by binary tree. This is in practice. It's much more robust. You just present it 3 by 3. Out degree 2 is not a restriction in practice. That's only what we can prove for out degree 2. This is 15 states. Each of them has 5 transitions out. This is what we train on, and this is what we estimate. And this is happening just in this brain model. Nothing special. And then, as far as the representation size is concerned, it's roughly the number of states. Okay, so in conclusion, coin flipping enables a brain-like mechanism to represent and learn probability distributions. It seems crucial to the brain's operation. It takes advantage of ambient noise, whether it's chemical noise or variability trials. Well, great, but how about, those things all seem so passé. How about generative model, right? So how about if I just present this brain model with a sequence of tokens? Each token might already have an assembly because it's a word and has an assembly. And then we ask it to start generating. So here, it's generating this. Okay, so this is like your, can somebody recognize what we trained it on? It's the poem called The Owl and the Pussycat by Edward Lear. Max picked this, and you can see it's not the original poem, but but we trained it on it 4 times, and then this is the generation. Every generation will be different. This is like your old trigram models, okay, where you have this. So it can babble. So we've got to the point where a brain model can babble. I mean, I don't know if, for those of you who've had kids, that was a very exciting point, wasn't it? So here we go. Okay, so so far it's statistical correlations, right? Can we go beyond this? How about structure, possibly longer range? Well, assemblies can be hierarchical. You can have assemblies of assemblies. This, you can read this, I want to conclude with this little experiment. So you see this. You can read this because it's at the rate at which the brain can read. In contrast, this is faster. It's about 12 times faster. The other one was 4 hertz, is about 50 hertz. So this was a beautiful experiment. This is the last thing I'm going to show by Popel. Here I'm presenting a sequence of words. May I ask you to read them? Yes.
Fans, blue, gas, it's, them, cat.
Okay, there's just one frequency your brain is emitting. Great. I mean, I measured it. It's once per word. That's all. It's only doing it once per word. Fantastic. Okay, if you could humor me one more time. Yes.
Bad cats, eat fish, new plan, gave, joy, little, boy, takes, roll.
I measured your frequencies. Do you know what they are now? You get 3 different ones. Yeah, this is the real experiment. They measured the frequencies, and you get 3 different ones. You still get the 4 hertz where you recognize every word, but you also get 1 at 2 hertz and 1 at 1 hertz. Anybody want to guess what those are? The 2 hertz is the completion of phrases, and the 1 hertz is the completion of entire little sentences. Very consistent experiment. So you can imagine the brain is creating these little trees. Bad cats eat fish, that's a sentence. New plan gave joy. And to be able to do this, you have to create these little assemblies quick enough. Well, how quick? Roughly 1 every 12 operations. Yeah, so the completion of phrases activates part of Broca's area. So yeah, in about a dozen spikes, you can create assemblies. And so that would say that you can create these little trees, sparse trees on the fly in this model. Okay, there are many research directions. I'll put this slide up so it's on the recording. And I'd love to know about all these things. And I'm putting that in very light colors because we are so far away from it, but maybe in the distant future. Yeah, okay. But one question, just the first question, is there a provable phase transition in cognitive ability based on connectome complexity? So when we went from deterministic to using this randomness, it turns out we had to scale up our sizes by about a factor of 10 to 20. Otherwise, we weren't getting enough fidelity. Okay? Whereas for the half-space learning, 1,000 neurons were enough. For getting this to work for Markov chains, we had to use 100,000 neurons. It still runs on anybody's laptop, but it's much bigger. But is this, what separates this, dolphins from us? Thanks to all wonderful collaborators, Christos, Dan, who you saw here earlier this week, Mike Collins, Wolfgang, Max and Maribel, who've been here the past 3 weeks, to you. So just want to say, we have this tiny working memory, right? We've seen this in the constitutive, tiny working memory. Very slow processing. I mean, some of us even slower. Very little energy usage, right? It's shockingly little energy usage. So many cognitive tasks, and surely we're missing some ideas still. So LLMs are exciting, but I think the brain is really the mystery. Thanks.
thanks for your talk. I had two kind of questions about whether you've looked at specific things. So one was about kind of how sensory inputs get changed into kind of word level information, because with assemblies, it seems like it's already kind of at the concept or word level. And I was wondering if you had thought about how like sensory percepts would form these like higher level assemblies. And the second, I was wondering if you had looked about like specific types of human pathologies, for example, with sequences, about how sometimes people can remember sequences, but not like individual words, whether there's specific components of this type of model where if you're missing it, you'll kind of get those sort of problems that we see with human patients.
For the second question, we're not there yet. The model is very simple, and I don't think we're able to model specific deficits. For the first, yes, we think of sensory areas themselves as areas, brain areas, with neurons that are specialized, but at the end of the day, they're still basically indicators. They're either firing or not firing based on what the neuron is supposed to be sensing. You know, in the visual cortex, it might be angle or movement or color in a particular location in the visual field. But yes, there's a brain area for each sensory.
I guess I was wondering kind of like how that integrates into the
so those project
level.
to higher level areas of the brain when they fire. When I see you repeatedly, there's a subset of neurons that are firing, and they project up. So I'm creating an assembly of you in the next level, which can then project somewhere else if it wants.
I think you asked this already, but so how does the capacity of the system grow with the number of neurons?
Yeah, so at the moment, for the theorems at least, it's only linear. So if you're trying to represent, it's linear in the number of assemblies. In principle, it should be, my guess is it should be quadratic at least, but I don't know how to do that. We don't know how to do that with a proof.
But even linear isn't obvious, right? Because the K probably grows with each concept you have to invest more in.
So if K is about root n size, then right, we do need the number. We can, as long as n is number of concepts times K. We're so up to root n concepts you can represent.
Very nice talk. Loved it. I have a question. One of the things that really work for deep learning is just like global optimization with backpropagation. Do you think that you really need global optimization of an objective to be more efficient learner?
So everything here, we
I
don't
know,
yeah.
everything in your model lack it. But do you think it's like a missing component to be efficient learner when you have not memorization of speech, text that you learn, but if you want to learn the entire language, then do you need it or not?
It's a good question. I don't know. It seems that the brain does have some global feedback, like dopamine and sort of everybody, lots of synapses are getting the same signal. We haven't modeled that yet or found a good reason for where it makes a difference, but surely it should be coming. We can simulate any computation in this model. That's what the Turing completeness says, but whether you can learn as efficiently as, say, machine learning systems do is unclear.
So what can't it do? I mean, I guess it's a Turing machine, but what's the simplest thing that you've tried to make it do in some straightforward way that you haven't been able to get it to do yet?
Oh, so it's a good question. So let's see. Well, this is not the most interesting answer, but we think of thought or a sequence of a train of thought as basically a sequence of sets of assemblies firing. You have a set of assemblies, next set of assemblies, next set of assemblies, and so on. So what is the next set is a function of the previous set in each area. We can get this running for 2 assemblies at a time. More than 2, it's not working in simulation and certainly not in theory. I don't know what's missing. And it seems like we are more than 2. I mean, we see lots of things that determines the next set of things, the next set of things, and so on. So this multi-track, that everybody's, that's sort of a concrete thing. Of course, it will never be able to tell you whether a program will stop or not.
You briefly mentioned phase transition at the very end of your talk.
Yes.
Does that mean you all of a sudden change the long-range correlations within the brain?
No,
something
what
like
I
that,
mean
or
is the ability to do certain tasks. You don't have it, and suddenly you have it.
So that's a correlation, huh?
As we see in species,
Right.
right? The question is, can this be explained by just brain complexity, or is there something more fundamental that needs to come in, some structure? Yeah.
Hi, quick question. Lovely talk, by the way. Could you comment a bit on how important the randomness in the graph is? You mentioned you're using this Hierarchical model, and you said that the results hold with high probability over the choice of the graph. So do we really need the randomness there if we use like a complete graph?
We tried to model it as deterministic assumptions, but it's not clear. I mean, one of the things we get from the randomness is this sort of expansion, which means that any subset is well connected to any other subset. But it seems like you need more than that. Because if you had some areas that were better expanders than other areas, you'd have a problem where you didn't have this ability to represent and converge to many assemblies. So it's unclear.
Okay, thank you.
Right at the moment, we do need randomness. Yeah.
Okay, thank you, Santosh. And I guess thank you, everyone. I think we're done. It's been a month. It's been amazing. Okay, I don't think we have to. We survived. I don't think we have time for any like scientific or personal, closing words, but I do have to say thank you. So thank you to my fellow organizers, Alison Gopnik and Doris Tsao, who are really like part of the force behind this, and Amanda Seed, Philip Isola, who was the only guy I have on Google Chat, so he had to do a lot of the work. Destin Cassel, Christos Papadimitriou, Antonio Torralba, and Shimon Urman. Thank you to Shafi Goldwasser and Sandy Irani and Sampat Kanan, who are the directors of the Simons Institute, who let us kind of hijack this very respectable place and bring in all the hackers and the philosophers and the biologists and the psychologists, et cetera, the neuroscientists. And then also to the staff, Caroline Winter, Atiya, Ashley, and Frida, who without them, you all would not be here in person. So thank you all, and we'll see you at dinner. See you next time.